Hi guys, I'm documenting the NE555 timer IC, which could be used to create many different timer related circuits. For example, um, the one I'm demonstrating today is the monostable 555 timer. In a future video, I'll demonstrate the bistable configuration and also the astable PWM modulation. So here's the result. So when I press this pin here, this pop-up button, this LED will light on, and it'll only light for a timed period before turning off. So I have a DC voltage source set at 10 volts, and when I press on this button once, like let go immediately, this LED will light on for 10 seconds. So let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There you go, and it turns off. So, how does the circuit work? Because I've somehow added a timer using an IC. So first, let's have a look at what the IC actually does and what the internals of the pins actually do. So this is the IC on the circuit board. It's the NE555 timer, and it's got 8 pinouts. So in this IC, there's a 5K, 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 5K voltage divider, which connects from VCC to ground, and they split the voltages up for 2 references, which is this one at 1/3 VCC and this one at 2/3 VCC. And they go into a comparator op-amp, which connects to the non-inverting input of the first op-amp, goes to pin 2, and then the inverting pin goes to pin 2, and then the non-inverting pin of the second op-amp goes out to pin 6. So what these 2 op-amps do is they compare the voltages of pin 2 with 1/3 VCC and then 2/3 VCC with pin 6. And by changing the voltages inputted through pin 2 and pin 6, you can get these op-amps to basically pull high or pull low. And these 2 op-amps are the inputs to a flip-flop. So a flip-flop stores the state, and it's I believe that the flip-flop being used is more complicated than just an astable 2 transistor config, because it's outputting it's got a Q and invert Q output. So what's happening is there's a set and reset pin that goes into the flip-flop, and when set is pulled high, the flip-flop will basically be at the state of 1, and then when reset is pulled high and set is pulled low, the flip-flop will have a state of 0. And this Q and inverted Q output is basically one is high and one is low depending on the internal state of the flip-flop. So the flip-flop is 1, Q will be high, invert Q will be low, and then if the flip-flop is low, then Q will be low and invert Q will be high. So there's a state that's being stored here based on what it was set previously, and this Q output is put to the output driver, which goes to pin 3, and then this invert Q output goes to a transistor, which then basically allows pin 6 to drain. Pin 7, to drain through the transistor back to ground. And you'll see where this is actually used later on in the video. There's 2 other inputs which are kind of strange, these pins. There's a reset pin, pin 4, and when this is pulled high to VCC, it resets the state of the flip-flop. And this is usually used to make sure that when we first turn on the power, that the flip-flop always is off, in the off state, in the zero state, I should say. And next is the control voltage. And this one goes to it's actually used to basically tied with a small capacitor to ground to short out any fluctuations in the supply voltage to make sure that these two voltage divider reference voltages do not, shake a lot when the supply voltage has any disturbances. And you'll see where this is, added in the future as well. So, yeah, let's look at how the monostable timer works with this 555 timer. So, I think one concept to realize why it's designed this way, why this IC is designed this way, is that basically by varying pin 2 and pin 6, you can set a state in the flip-flop, and then you can add a timing component, for example, via capacitor, to one of these, right? And because it takes time for the capacitor to charge up or discharge whatever voltage required to get back to an original state, the flip-flop will lock the circuit output to one of the states until the capacitor does its job, and then these states change again, changing the flip-flop. So that's how ultimately the timer works. We have to basically set a state on the flip-flop and then wait for the capacitor to either charge or discharge to set another state. So essentially, when I press this button here, on button down, it immediately sets the state of the flip-flop such that the output pulls high. And then when I lift my finger off of the button, the circuit is designed in a way such that the capacitors take time to reset the state again. So let's look at the actual timer circuit and what's going on. It looks a bit confusing at first, but it's actually really simple. So this pin 2, which is the non-inverting input of the first comparator, is connected via a resistor, and this resistor is usually typically very large, to the VCC. And this is the switch, so it's by default off. And so then by default, pin 2 just has the voltage of VCC because this is an open open circuit, and the current has nowhere to run, so it becomes the same voltage as VCC. And likewise, initially, the pin 6, which goes to the non-inverting input of the second comparator, is also at is not at VCC actually. This is at close to ground, 0.2 volts. And you might be asking, oh, why is that? Because the capacitor, assuming it's steady state when the switch is open, the capacitor is basically like an open circuit, right? So this should be at VCC because there's nowhere for this current to run. But actually there is. There's this pin 7. So pin 7 is connected to the transistor. The base, it's connected to the emitter, the collector emitter of a transistor. So it drains through the collector into the emitter into ground. So the current actually flows this way. So through VCC, through this resistor R1, and then through pin 7, through this transistor, all the way to ground. So therefore, the voltage at this junction is just going to be the voltage of the collector of this transistor, which is in saturation. And that's going to be at close to 0 volts. I think it should be 0.2 volts, actually. So then you got pin 2 at VCC, and then pin 6 at basically ground. And what that means is both of these comparators are going to be pulling low. because in order for the first comparator to pull high, the non-inverting input, the negative terminal, needs to be lower than 1/3 of VCC as determined by this voltage divider. And it's not. This is a high voltage at the non-inverting, so it pulls low. Likewise, for this one, the non-inverting input needs to be higher than 2/3 VCC, which is determined by this voltage divider on the negative input terminal of the comparator. But it's not. This positive input is close to ground, so therefore this one also pulls low. So both of these comparators pull low in the open configuration, in the open switch configuration. And because of that, the flip-flop is basically what it was before, and because it's tied to this reset pin, it's going to be at 0. It's going to output low. So basically this out is low when the switch is open. And so you might be wondering, well this transistor, why is it in saturation? That's because the base of the transistor is tied to the inverse Q output of this flip-flop. So when the flip-flop is outputting low on Q, right, the output is on Q, this invert Q output is actually high. So therefore the transistor is in saturation because the base is tied to this invert Q. Yeah, so then what happens when I press the button? So when I press the button, this thing closes, and on closing, immediately what happens to pin 2 is pin 2 basically drops to ground because it's now ground referenced, right? The current goes through here and drops through R2 and goes straight to ground. And so therefore, comparator 1 pulls high because now the negative input is ground, the positive input is 2/3 VCC, which is higher than ground. So the set comparator, which is going to pull high, is going to set the flip-flop to high. It's going to set it to on, basically, to the 1 state. And therefore, what happens is the output is going to be high, right? Because the output is the non-inverted Q of the flip-flop output. So on pressing this switch, immediately my LED is going to turn on because this comparator is going to pull high. The set comparator, is going to pull high, sets flip-flop to 1, and then out is going to be high. Now, there's another thing that's going to happen. When the out becomes high, so Q is high, the inverted Q is going to be low now. So therefore, this transistor is going to turn into cutoff. And when the transistor turns to cutoff, current can no longer flow through pin 7, right? So therefore, VCC is not going to be able to discharge any current through here, through pin 7. So then what happens is we should expect that pin 6 should pull high immediately. And because pin 6 is tied to this non-inverted input of the right-hand side comparator, we expect the comparator to pull high again, which resets the flip-flop. But actually, this doesn't happen immediately. Why? Because there's a capacitor C1. What happens when the transistor turns off immediately as we press this, as we turn on this switch, is that this capacitor is going to become basically a current sink to the current that usually were flowing through the transistor. So it's going to actually try to start charging up this capacitor until the plate facing pin 6 of the capacitor reaches 2/3 of VCC. So there's some timing delay because of this capacitor charging up. So it's basically close to ground. You turn the switch on, this transistor turns on, and the capacitor starts charging. And as it charges past 2/3 VCC, what happens is then this comparator then turns on, and it sends a reset signal to the flip-flop. And so you can configure what this timing is by basically looking at the capacitor and the series resistor, because it has now the only way to charge it is now through the series resistor at R1. So it's basically an RC equation that looks like this. So this is the RC equation. It's the voltage across the capacitor over time is equal to the supply voltage times 1 minus e to the power of negative t over RC. And when you do some algebra and simplify things, it turns out that the time it takes for this pin 6 to charge up to 2/3 VCC is RC times natural log of 3, which is about 1.1. The other thing to note is that if we press and then immediately release, the expectation is that the output is going to light up straight away, because this comparator straight away starts to output high, flip-flop turns high, and this comes, the output is high. And then when we release, the comparator, the set comparator is going to be low. But because the reset comparator has to still wait for the capacitor to charge, at the stage where we just press and release, this comparator is still outputting low. So then this comparator goes high, low, and this comparator is low the whole time. So therefore the flip-flop will go high and then stay high until 10 seconds pass. Then this comparator pulls low, and now the flip-flop gets switched to low, and then out becomes low again. So then you expect a 10-second flash of basically 10-second on time for the LED connector to out, and that's what we see. An interesting question is, what happens if we don't let go straight away? What happens if we press the button, but then we hold it for 10 seconds? So then what happens is, what actually happens is after 10 seconds, the light is still on, but then as soon as we let go of the light, of the button, the light turns off straight away. So let's demonstrate that. So if I press the button, oh sorry, I need to turn on the voltage first. So I press the button, it lights, I'm going to wait 10 seconds, 2, 3, 4, 5, 6, 7, 8, 9, 10. The light's still on, but as soon as I lift my finger, it should now turn off straight away. There you go. So why does that happen? So first of all, why is it that after 10 seconds of holding the switch, the out is still on? The LED still lights. The reason is because at that stage, both of these comparators are outputting high, right? Because we haven't let go of the switch, so this comparator outputs high. And then the timer has finished on this capacitor, so this comparator also outputs high. And when both comparators output high, the set and reset pins of this flip-flop are both high. The flip-flop is actually going to prioritize the high state. So you can actually design a flip-flop to prioritize one state or the other. So when both the set and reset pins are high, this flip-flop is designed to stay as the high state. And then when you let go of the switch, this comparator straight away drops low. And therefore it resets straight away because this is already high. We already finished the timer, and so therefore the flip-flop immediately turns low when you let go. And that's the behavior that you see as expected. There's another question, right? Which is, why is it that the discharge of the capacitor is so quick? So for example, when we switch on the switch, the capacitor charges very slowly through R1. But when we let go of the switch, after the holding it for more than 10 seconds, why is this discharge so quickly? Why, like, because doesn't it have to discharge through this resistor? The reason is no, because it discharges through pin 7, which goes through the collector emitter junction of this transistor. So the resistance is basically minimal, right? So that's ultimately what drives this timer, is that the time it takes for the capacitor to charge is far longer than the time it takes for it to discharge. So there you go. Once again, let's just show this one more time. It's a the timer circuit. So basically, by changing this capacitor and the value of the resistor, because it's a series RC circuit, we can change the time it takes for this LED to stay on. So one click, and yeah, I've made it such that the two values approximately will take 10 seconds to turn off the light like this. All right, great.